Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
So now we move on to another important aspect of dislocations. What are the aspects we are going to see now? First, when a single crystal is deformed, slip occurs with shear offsets of thousands of atom distances on relatively widely spaced planes rather than uniformly throughout the crystal. You see, when I started this chapter, I was just mentioning that we are looking at this dislocation and its description because the primarily elasticity theory of elasticity deals with most of the calculation of energy and the stress field equations. So that's why I wanted to bring it in the beginning itself. But now we are concentrating on mechanics. Now that we have some idea about the dislocation and its nature and other details of stress and energy, so on, I want to just complete some introduction on the dislocation, motion, and mechanics. But then, when you talk about mechanics, then it will involve other aspects which we have not looked at. For example, when we talk about dislocation, motion in a crystal system, then we will talk about deformation, which we are yet to see. But then, what I want you to just understand this is, suppose if you are getting some idea in now itself as a background, and this will be easy to, it will help to understand the plastic deformation or plasticity discussion, which we are going to do it in the subsequent classes. So some of the new terms will come here. For example, work hardening. The term work hardening will come, but don't just get worried about that. But we will bring it explanation then and there wherever it is required. So just I just want to give this information before we get in describing this dislocation mechanics. So we are now here talking about the single crystal deformation, and which occurs through slip, a mechanism called slip with the shear offsets, right? So this is how most of the textbook describe the slip. So these are the crystal slip steps, small steps, and this is called the slip line, and this is the shear stress direction, and some approximate numbers are given. How many atoms will be involved in a step or bunch of steps? 100 atoms diameter, 1000 atoms diameter, and these steps together, they are called slip band. Okay, so we'll get into the details when we start discussing the plastic deformation. But then here we are bringing the context because we are looking at the dislocation mechanics. Why does slip not occur uniformly at an atomic scale? So this is one question. Okay, suppose why are we looking at dislocation mechanics? There need to be some valid reason, right? So this is one of the reasons. Why does slip not occur uniformly at an atomic scale? So here the slip bands are localized. Okay, there is a gap between this slip band and the other slip band. And why there is a heterogeneity here? Okay, that is what the question means. Okay, though this is not exhibiting the atomic scale image, but if you just imagine that all the these number of atoms are shown here, it will not show the uniform different slip. Okay, there will be some gap here, and there is a gap here, and then steps come. This kind of steps happens with some intervals. So why does it happen? Secondly, the cold working increases the dislocation content of crystals, even though dislocations must run out of the crystals. Where do the additional dislocation come from? So this is one point we have to understand first. What is that? Cold work means you deform at low temperatures. okay, much below the, recrystallization temperature and so on. So much, for example, room temperature deformation. That kind of deformation increases the density of dislocation. And you have to understand one important point. While these crystals undergo the deformation, especially a plastic deformation at room temperature, though the defect density increases, but most of the defects run out of the crystal system. The velocity by which the dislocation moves is pretty fast. We will discuss that when we come to the deformation behavior. So most of the defects which get generated will run out of the crystal system. Okay, that's what it is written here. Then, if you assume that most of the crystals, get rid of this dislocations during cold deformation, then how the dislocation density get increased? So where do the additional dislocation come from? These are all the other questions. Third, the yield stress increases as the number of dislocation increases, even though without any dislocations. The strength would be even higher. Okay, so this is something you have the clue now, because in the beginning of the dislocation chapter, we looked at the strength of the bond calculation, theoretical value of the bond strength, right? So even without dislocation, the strength must be very higher. But the yield strength increases as the number of dislocation increases. So there is a difference. So why increase in dislocation density helps or influence the yield stress is the question mark. And why does the yield strength increase with the dislocation density? Yeah, this is what I just said. To answer these kind of questions, the dislocation mechanics is looked at more critically. So one of the important or primary mechanisms by which the dislocation multiplies into the crystal system is popularly known as Frank-Reed sources. Frank-Reed source. So what is this Frank-Reed source? Look at the schematic here. This is a perfect crystal. You are looking at the slip plane in the middle of this crystal and the dislocation line AB, and the shear stress is applied in this direction. So first off and this bottom off, these two are pulled in opposite direction. So then what will happen to this AB? That is the question. So what happens in the first stage? So you are seeing this dislocation line which is getting bowed a little bit as the stress slowly starts increasing. The dislocation line getting bowed. The distance between these 2 points is D. And as the stress continues to increases, the bowing becomes more significant and the radius becomes more and more. And then what happens? The extension of this dislocation bowing becomes extreme at this situation as the shear stress increases. And finally what happens is this two ends, okay, this the enlarged loop try to come together and they bring to this kind of a contact, and then it becomes another fresh dislocation line, leaving a huge loop around it. Okay, so yesterday we have seen, right, a dislocation encounters an obstacle and this is how it bows, right? It is like a line tension. We have looked at the energy force balance and then we formulated an expression to calculate this, right? So similar mechanisms. So if you just imagine this this mechanism continuously operating, that means what happens? This kind of mechanisms will leave a loop after loop as the deformation proceeds, or the crystal is experiencing the shear stress continuously. This kind of dislocation source will generate a lot more dislocation inside the crystal, in spite of lot of dislocations run out of the crystal lattice during the cold deformation. That is how we have to understand that. Okay. So Frank-Reed source explained how the number of dislocation increases with the deformation. A quantitative treatment of the operation of Frank-Reed source can be made by considering the balance of forces acting on the bowed segment of the dislocation. This is all done. The applied shear stress tau causes a force tau dot BD, and where D is the distance between the pin and the dislocation. The line tension of the dislocation, energy per length, that we know. This we have already seen. It's a repetition here. So the line tension T is GB squared, and if you consider this theta part, then it will become GB squared sine theta, and this is the TBD is the line tension here. So UL is equal to GB square acts parallel to the dislocation line and tends to keep it from moving. So considering both ends, the vertical component of this force is 2 GB square sine theta. So this is vertical part. The force reaches a maximum 2 GB square when the dislocation is bowed into a semicircle, that is theta is equal to 90 degrees. Equating these two forces and assuming the shear stress is parallel to B, then we get this shear stress BD is equal to 2 GB square. It's nothing but 2 GB by D. It is the same equation what we have already derived the last class. So what does it give? What is the physical meaning of that? The stress necessary to operate the Frank-Reed source is inversely proportional to the size of the source D. Okay. So the shear stress is inversely proportional to D. Okay. So if the D is small, that means the two obstacles are placed very closely, then accordingly your shear stress will be varied, right? So that is what it means. So the next important aspect of this dislocation mechanics is dislocation pile-ups. So this again we will use this term quite frequently in the deformation behavior of polycrystalline materials as well as single crystalline materials. So there is a obstacle for a dislocation motion, and then whatever the dislocation which get generated inside the crystal get piled up against this barrier. This kind of situation, when a dislocation from a Frank-Reed source comes to an obstacle such as a grain boundary or hard particle, they tend to form pile-up. Because they are of like sign, they repel one another. So eventually what happens? That's our interest. The total repulsion of the dislocation by pile-up is the sum of the repulsions of each dislocation in the pile-up. With the n dislocation in the pile-up, the stress on the leading dislocation tau n will be n times the tau. It's a huge force if you add up all of them. It takes a relatively small number in a pile-up to effectively stop further dislocation movement. A pile-up creates a back stress on the source, so that the stress to continue to operate the source must rise. So this is very important idea, the back stress. The back stress also has a huge role to play in explaining some of the dislocation mediated plasticity. We will be using this term quite often, especially in the work hardening theory. Okay, so the pileup, it creates a back stress on the source. Okay, so that the stress to continue to operate, the source must rise. So this again, as I mentioned, this will be useful. This parameter will be useful while we are looking at the work hardening behavior. This higher stress allows other source of slightly smaller spacing D to operate, obviously. So just previously we have seen, if the D becomes small, you need a higher stress. So when the higher stress comes, then even closely spaced particle also will generate Frank Reed source of dislocation. That's an idea, right? Cross slip. This is another mechanism by which the dislocation moves. And if you look at this schematic, this is nicely shown here. There is a 111 plane where the dislocation line is there and the budget vector is there, the direction of motion is there. And there is another plane which is not of the same level but at with some angle. So the dislocation, the screw dislocation can move, and very easily it can just glide on this angular plane and then move on to the next higher level plane like that. So that is the description of successive positions of dislocation, especially a screw dislocation. Okay, what are the implications? We will see one by one. So when a screw dislocation gliding on one plane changes to another, it is said to undergo cross slip. In principle, screw dislocation should be able to cross slip with ease to avoid obstacles. Please understand, we are now talking about screw dislocation, not edge dislocations. The previous slide we showed that pile up, we showed the schematic only for edge dislocations. So the screw dislocation will easily avoid the obstacle, unlike edge dislocation. That's one information you can keep. So what are these schematics? This is a cross slip of a dissociated screw dislocation. Suppose the two dissociated screw dislocations are shown here, and these two planes are intersecting planes of similar nature. But then how these dissociated dislocations will try to move in these kind of circumstances is the question. So if the dissociated screw dislocation, they will not just like that cross slip, but it must first recombine. Okay, so it must recombine this way. It has to recombine and form a single unit dislocation. Then dissociate into cross slip plane. Okay, like this, and cross slip, and then finally again dissociate before it finally can glide onto the cross slip plane. Okay, so again recombine, cross slip, dissociate, and then glide. So this is again a partial dislocation on a different level now. Okay, so it is almost looking like two partials which we started here. Okay, so this the dynamics is again an energy criterion. So this is just one examples how screw dislocations move. A screw dislocations is separated into partials connected by a stacking fault. This we have seen already, right? Two partial dislocations, they are connected by a region of faulty region. It's called stacking fault. Both partials cannot be screws. They must recombine to form a screw dislocation before they can dissociate on a second. So this is what we have just illustrated here. So this is another a schematic of double cross slip. Okay, the segment of dislocation on the top plane can act as a Frank Reed source on that plane. So this is another example of a cross slip, but it is a double cross slip. Such recombination increases total energy, and this energy must be supplied by the applied stress aided by the thermal activation. So this point, what we are talking, not pertaining to this. This is something, the previous description, recombining of these two partials will increase the total energy. So how much energy is required depends on the degree of separation of the partials, and therefore on the stacking fault energy. This also we have seen. Okay, the separation between the partials decides the amount of stacking fault energy. Okay, if the stacking fault energy is high, the separation of the partial dislocation is small. So the force required to cause recombination is low. Okay. So yesterday we started with the partial dislocation, and then I raised one question. The title I showed was partial dislocation in FCC crystal system, right? Then I raised the question, why not in a BCC crystal system? Then I mentioned it's not that partials are not there in BCC, but they have very unstable configuration. Even if exist and recombine, they exhibit very unstable configuration. Okay. So this is one idea. So very high stacking fault energy material, but in terms of aluminum, they don't show partials, because what happens if the energy is very high, the force required to cause a recombination is very, very low. So when such a system prevails, no partial dislocation will stay stable. This is the idea we have to remember. Okay, later we will use this based on this criteria, and when we connect the stacking fault energy with the deformation behavior and classification, you will see that we will classify materials based on this dislocation morphology or mechanics, so-called baby slip material, or I would say planar slip material, planar slip and baby slip. So we will see all of them. So they are all connected terms. So that's why I'm just bringing it here. In metals of high stacking fault energy, example aluminum, cross slip occurs frequently. In metals of low stacking fault energy, like a brass, the separation of partial is large. So this is one classical example, aluminum and brass. Okay, so the aluminum will have the stacking fault energy in the order of 200 millijoules per meter square, whereas brass will have close to single digit 8 to 10 millijoules per meter square. So the recombination requires huge energy. So that's why these partials remain stable. Yeah, high force is required to bring them together. So cross slip is rare. So the cross slip is rare in materials with the low stacking fault energy. That is why they are called planar slip. They exhibit planar slip. The slip occurs only in the plane. That means that dislocation activity or glide motion confined to individual planes, not the cross slip. In the other way, we can say that in a very simple terms, the three-dimensional mobility of dislocation is highly restricted. So this is also another way of looking at it, right? So when the three-dimensional mobility of dislocation is facilitated, then the dislocation will climb through cross slip very easily, and you will see all sort of dislocation morphology, long extended dislocation, right? Like tangles and cells and so on and so forth. We will see one by when we come to description of the deformation of the structure. So I think I will stop here. We will, and the next topic I want to discuss is dislocation intersections. Just few examples of dislocation intersections where it will contribute to several microstructural, I would say, stability, and also it controls a lot of mechanisms, phase transformation mechanisms, and so on. We will see it in the next class. Thank you.